Okay, so we are on day 4, and we are talking about adapting our integration techniques to calculate area between curves. So up until now, we have calculated the area, I'm going to use air quotes here, the area under the curve, which really means the area, like if we look at this expression for the fundamental theorem of calculus, from A to B, let's say A is over here and B is over here, then what we're really talking about is the area from A to B that is between the function f of x and the horizontal axis. So in this case, because I dipped below the horizontal axis, I actually have 3 regions that I would be calculating. Like if I did a math 9 on my calculator, from A to B, it knows that f of x dips below a little bit, and it will accommodate for that area. Okay, but now we're talking about between curves. So that being the case, and you saw this in the video in your notes, if I have an f of x and I integrate f of x between a and b, in this case, it looks like between 1 and 5. Let's just pretend that. Then if I integrate f of x from 1 to 5 here, I'm going to get a value that represents the area of that green shape. Likewise, if I have a function g of x and I integrate it over the same domain from 1 to 5, then that value I get is the value of that red region between the function and the horizontal axis. But sometimes we don't want to just get this region that's bounded on the bottom by an axis. Sometimes we want to get the region that's bounded by an upper and a lower curve. And so what we literally can do is we can melt those two together and say, well, if I want to know that region in the middle, let's call that the blue region, then I can just take the green region and subtract the red region from it. It's literally like taking the green region and then taking a scissors and cutting out that bottom portion. Does that make sense? Okay, so I mean, it's not rocket science, but it's a nice conclusion that we don't have to be bound by this horizontal axis anymore. So we can use these things, like when we talk about integration applications in calculus, we can say things like, hey, you know, maybe f of x is the rate at which snow is falling in a snowstorm. So snow comes down really heavy here for a while and then kind of tapers off, and then it picks up again. And maybe this is the rate at which I'm shoveling snow on my driveway. You know, I come out, I'm kind of irritated that I have to shovel snow, so I'm kind of going kind of slow. And then I kind of hit my stride here. I'm nice and warm and I'm kind of enjoying being out in the snow. So I'm shoveling really fast. And then I start to get tired. So I start to slow down in my shoveling again. And so that region in between would represent what then? If this is how much the snow is falling, and this is how much I'm taking away, what is that blue region representing? Yeah, it's what's left. It's what I can't keep up with, basically. Does that make sense? Okay, so that in terms of applications, they like to use it in those types of applications when we have something accumulating and then something taking away from that accumulation. So snow falling, me shoveling. Something filling a water tank with a leak in it, so something's draining out. Those are other scenarios. Something, you know, filling a hopper full of grain while you're farming, and then simultaneously emptying from the bottom to feed your cattle. How much is left in the silo? Those sort of scenarios start to pop up. And so this gives us a way then to find that without having to really adapt too much the integration techniques we have. Is that making a little bit of sense? Okay, so fast forward to the I just wanted to get that animation in there. Fast forward to the takeaways. Away from current slide, there it is. Okay, hopefully this is fairly intuitive. Smiley face. The setup is where the points are, so make sure you have all the requirements. So what I mean is when you are looking at that general expression of the integral from a to b of x minus g of x dx, when I say the setup, because a lot of times what they'll do is, especially on no calculator ones, they'll say set this up but don't solve it. They're just grading you on your setup. Okay, so they need things like if f of x is a polynomial and it's got several terms, they want that in brackets. And you're going to subtract another polynomial, they want that in brackets so that you are distributing that minus sign on to every term on that g of x. Dx problems, like we just saw, they sweep the area from left to right, like we're normally associating with integration. This means it's top function minus bottom function. That makes the difference positive because the top is always a bigger value than the bottom. These are our functions in terms of x, but we can also sweep the area from bottom to top. And so in this case, these would be dy problems. So for instance, we could have a region that was like a sideways parabola on a vertical line. And what's the area of this region? You know, from C to D. And I don't think it's too hard to imagine me taking the board and rotating it 90 degrees to make it go left to right instead of top to bottom. Okay, but the way we can adjust that is we can call that a dy problem, and we can take these functions, you know, like this is probably like equals y squared plus 6, right? And maybe this is x equals 2. But if we get the function as x equals and leave it in terms of y, we can integrate it like we integrate everything with respect to x. Okay. And again, now I'm taking, instead of top minus bottom, I'm going to take right minus left, because the right function is the bigger function. It's farther along the x-axis. And so if I go right minus left, I'll always get a positive difference. Even if I'm over on this side of the vertical axis, if I take right minus left, you know, if this is -7, this is -9, -7 minus a -9 is a positive difference. Right? I'm still taking a difference of a bigger minus a smaller number. So that adaptation serves us well because we always get a positive answer. We know area is always a positive value. Right? We know that from geometry, area of square or anything like that, right? We always get a positive answer. Okay. For today, the focus is on functions that only cross twice. And most will come with graphs. Most will be quadratic/line combos. Okay, so if that's the case, going back to a dx problem, it would be something like cross twice. Quadratic line combos. Let me think about that for a second. Got to look at the syllabus here for a sec. Yeah, okay. So cross twice, like quadratic line combos. So for today, it's going to be like this, right? Or maybe it's like this. Okay, they cross twice. They create one enclosed region. And we have to set the quadratic and the line equal to each other to solve for A and B. points of intersection. Sometimes we have to do that. Okay. And then I think getting into Wednesday, or our next class is Wednesday. Yeah. We're gonna start talking about what happens when they intersect several times, and all of a sudden, in one part the curve is on the top, and in the other part maybe the line's on the top, right? So what happens when we get into something like maybe a cubic and then a line, and then now we have this on top, and we have a swapping here. Now we have to be really careful about splitting that into, if we're doing this by hand, splitting it into two integrals, so we have the right f of x and g of x. But we'll get into that on Wednesday. Okay. So how is integration adapted? It's a long answer to the summary question. The area is found mathematically by taking upper curve minus lower curve. Probably is the operative phrase. Upper curve minus lower curve for dx problems, right curve minus left curve for dy problems. Kind of like that better. I'll write that on the board. So upper minus lower for dx, right, minus left for dy. That will always result in positive differences. Okay, so we've got day 4 topic questions and a couple of cons, and then day 5 notes for Wednesday. So I'll come around and check in with you, see how you're doing. And just touch base with you.